Hello everyone. Today I introduce the proposed method, adversarial dictionary learning for speech enhancement. Why we need to do the speech enhancement? Because with the pervasive use of the mobile devices and the smart home products, the speech enhancement has become increasingly important as a front end of the speech recognition, which can produce high quality speech signals for the back-end system under the adverse environment. However, the conventional speech enhancement approaches suffer from the obvious performance degradation when the speech is contaminated by the non-stationary noise under the real-world adverse environment. And in this paper, we utilize the generative dictionary learning-based method. And the generative dictionary learning-based speech enhancement method was proposed for noise reduction based on the sparse representation of the speech and noise magnitude spectra. The noisy speech is modeled as the clean speech plus the noise. Then we utilize the STFT to obtain the magnitude spectrum of the of the noise speech, which can be sparsely represented by a joint dictionary, and the sparse decomposition method can then be utilized to compute the sparse coefficient matrix, which can be used for the clean speech recognition. The original GDL method employed the K-singular value decomposition algorithm in the learning stage to train the speech and noise dictionaries, respectively, based on the speech and noise training datasets in the time frequency domain. At the enhancement stage, noisy speech is able to be sparsely represented by a composite dictionary, which is constructed by concatenating the speech and noise dictionaries to produce the sparse coefficient matrices of speech and noise. The speech magnitude spectrum matrix can be estimated through the product of the speech dictionary and its corresponding sparse coefficient matrix. Time domain speech signals are then synthesized by applying inverse Fourier transform to the estimated speech spectrum. However, the enhancement performance of the GDL method relies on the coherence of the dictionary to their corresponding signal classes, and the mutual coherence to the other signal classes. The high mutual coherence results in a perverse distortion to the speech quality, named the source confusion. And the modified coherence-based dictionary learning method here refers to the MCDL method was proposed to introduce a post-processing step named atom correlation to the trained dictionaries from the GDL method so as to reduce the source confusion, but the performance is still not that satisfying. The keys of the GDL-based speech enhancement methods are the sparse coding and the dictionary learning. For the sparse coding, we utilize the ADMM algorithm to solve the optimization problem of this kind of style, and the ADMM algorithm alternates among the following steps to estimate the corresponding variables, and this algorithm is also a very important step in our proposed method. And dictionary learning, dictionary is another key step. Dictionary learning aims at utilizing a large-scale training dataset to train an autocomplete dictionary so as to capture the internal structure of the data for sparse representation, which is usually based on the following optimization problem. And for here, the matrix D is composed of the data, and the psi is the dictionary we need to train, and the theta is the corresponding sparse coefficient. And for here, the constraint, the psi j is the jth atom in the dictionary psi. And for our proposed method, the speech magnitude spectrum matrix S can be modeled as the addition of the low rank matrix LS and the element, which can be sparsely represented by the speech dictionary psi S and the corresponding corresponding sparse coefficient matrix zeta S. And we also make a similar assumption on the modeling the noise, like this here. And for here, the N represents the noise magnitude spectrum matrix, the noise spectrum matrix, and the Ln is the low rank matrix for the noise, and the psi n represents the noise dictionary, and the zeta n represents the sparse coefficient matrix for the noise. And in the training stage, we for the speech part, and the purpose of our proposed method is to train the speech dictionary, which presents lower motor coherence to noise. And in order to achieve this goal, we extract the matrix LS from the speech magnitude spectrum matrix, and then utilize the residue RS to train the speech dictionary. And then we propose to utilize this kind of discriminator to pick out the atoms in the noise dictionary, which are highly correlated with the speech, and we utilize this optimization to find out the elements from the speech which are highly correlated with the noise, and then we utilize the residue to train the speech noise. And for the noise part, we also do the similar thing to the noise, and we extract the part in the noise which are highly correlated with speech, and then utilize the residue to train the noise dictionary. And we also utilize this kind of optimization technique to find out the element in the noise which are highly correlated with the speech. And thus, in the training stage, we follow these 3 steps for both speech and noise. At first, we find out the low rank matrix LS and Ln based on the above mentioned 2 optimization problems, and then compute the residue matrices RS and Rn respectively for the noise and speech. And then utilize both residue matrices to train the dictionaries for speech and noise. Here we represent as the psi S and the psi n. And because all these kind of steps are alternated with each other, so therefore we call this adversarial dictionary learning, and which results in the dictionaries that are lowerly correlated with each other. And after we have the well-trained dictionaries, and then in the enhancement stage, the noisy speech is also transformed into the time frequency domain, while the STFT, and then the noisy speech magnitude spectrum matrix can be written as this. The matrix L here is the addition of the two low-rank matrices LS and LN, and it is also a kind of low-rank matrix satisfying this constraint. And the matrix psi here is a joint dictionary, which is a concatenation of the speech dictionary and the noise dictionary, and this is the sparse coefficient matrix, which consists of the sparse coefficient matrix for both speech and noise. And then we propose this optimization problem to estimate the low rank matrix L and the corresponding sparse coefficient matrix zeta. And the above mentioned optimization problem can be solved through iteratively alternating between two subsequent problems. That means at the tth iteration, we need to solve these two subproblems. The first subproblem is used to compute the sparse coefficient matrix, and the second problem is used to compute the low-rank matrix. And the first subproblem can be solved via the ADMM algorithm, and the second subproblem can be solved through the SVD. And then after we have the solution, the speech and noise magnitude spectrum matrix can be estimated as this. And then as we have the noisy speech, as we have the magnitude spectrum matrix for the speech, we can do the IFT to this, and then we can get the speech signal in the time domain. And we use the timid corpus as the source of the clean speech. And noise used in the training are bubble, white, and HF and the factory. And because of the space limit of the paper, we just present experimental results for the unseen noise, including subway, restaurant, airport, exhibition. And we tested 4 kinds of SNR, and the sampling rate is 8,000, and we utilized the Hamming window. The overlap is 50%. And this table illustrates the PESC scores for different methods for the noise types. And the proposed method can make the average improvement of 0.4 on PESC for the unseen noise, while the comparing method cannot lead to any improvement under the unseen noise conditions. And for the STOI scores, our proposed method can still guarantee the improvement, like the average of 0.5 compared with the traditional method for the unseen noise. This is all about our proposed method for speech enhancement. Thank you.